Ladies and gentlemen, good morning. It's a great pleasure and an honor for me to be here at the ACA in Singapore. I want to give you some ideas and some overview about a new topic for new jointing techniques for large-scale timber structures. And when I saw the presentation of Mark, I noticed we have a link between both presentations. You will see later. So this structure here I put on the front page. This is the largest timber structure in the world right now. This is the Parasol Metropole in Sevilla in Spain. It's an exhibition multifunctional building, and the roof looks like this. We have like a waffle structure, and this is made of LVL. And of course, the weather condition, we have a coating. And for this structure, the difficulty is how to connect all those plates together. So I'm talking about the structure more than 100 meters. So always the joints in timber engineering are those points who decide how a structure could look like. So I want to give you an overview about traditional jointing systems, and also we had in research developed a new jointing system for large-scale timber structures. First, I want to show you some modern structures. They are well known in the world. We have here, for instance, a very traditional structure. This is the Japanese pavilion in Hanover. This is a bamboo structure, and it's jointed together here with the traditional Japanese technique. A bit more sophisticated here, truss structure. This is in Wengels College in UK. We have here quite a large truss structure. Or maybe this bars in Bad Dürkheim. This also in Germany. This is a sole bars. And we have here, this structure is made of glulam. So we have a glued structure and also mechanical fasteners. Or for instance, this is a gymnasium. Here we have a grid shell, and this is connected together with mechanical fasteners. And this one is a glued. No, not a glued structure. This is a nailed structure with only single lamellas put together crosswise without any further connecting. Only in some points they put nails inside. So you can see in timber engineering nowadays we have a lot of big, nice structure and some architectural eye-catcher. But the problem is how to connect this. So another part of timber engineering is the construction with solid wood and with hybrid structures. When I'm talking about solid wood, that means we have solid walls and slabs, no single small member. We go for the mass, and here you can design structures like this. We have here a research project and finished already in Melbourne on the marina, a lot of buildings, and also in the UK. In recent years, it's getting quite common to do composite structures, because if you have a composite, you can pick the favorable parts of each building material. For instance, here these are it's a timber concrete composite slab, the timber works in tension and the concrete in compression, and is connected by shear connectors. So with this system, you can have some nice touches of the of timber in the rooms, and also you have the full advantage of the composite action in the slab, and you can build here quite a large span in office buildings, for instance. So when we compare both structural types, we have here the composite structure. This is less than 20%. So you see the timber engineering or wood construction are not that advantage focused. They are still a bit classic, traditional, and a lot of structures built with trusses. So we have here a modern building. It's a multi-purpose hall, and this is made also with trusses. And you see here on the right sketch, we have a 3D joint. So the difficulty here is how can we put 1, 2, 3, 4, 5, 6, 7 different trusses in one point together. Another example here, this is an exhibition hall in Frankfurt. It's a new built one, and here you can see the scale. This is one construction worker is about 180. So we have here a height of the girder about 4 meters, and the length is about 70 meters. And if you have this length of the structure and the heavy snow, and you have the wind loading, and you have also the loading from, depending on what's going on in this exhibition hall, you need to put the heating system on the ceiling or whatever, you have additional loads. So these single points where the trusses and the studs connected get very high loading. So, and this is the problem, because wood as a structure material has 3 different directions and 3 different strengths. Parallel to the crane, we have the highest one. It's like a fiber reinforcement in concrete. And if you go perpendicular to crane, there's only the lignin. This is the substance gluing together all the fibers, and this is very weak. So we have the stiffness and strength perpendicular to the crane is about 1/5 parallel to the crane. So we need to take this into account when we designed such large-scale structures. So what kind of joints are used in common? First, nail plates. Nail plates are very common for roofing constructions in houses because they are fast to assemble and quite cheap. And the disadvantage is you have only small sections. That's why you have limited span. And also the aesthetic is doesn't look nice because you have the raw sawn lumber here, and then they just put the nail plate outside. So if you have the metal connector outside, there's another disadvantage. This is fire. So if you expose this structure to fire, you need to be careful. So you need to do the design for the fire resistance. So for larger scale structures, on the building side, normally we use dowels. The dowels here can be simple drilled in the timber, and you have here some metal plates inside. And when I'm talking about fire protection, we can do this here as well, because we can do the drill hole coated with timber maybe, or something else. So the full joint is within the structure. So advantage here, we have a multi-lap joint. That means the forces from the single members are divided by the laps. And we have a ductile behavior in this joint. No brittle failure. And fire protection is possible, I mentioned already. Disadvantage, if you look carefully here, we have a high assembling effort. So why telling you all those things about the connections? We have developed, together with architects, a new type of joint. This new type of joint is using new type of material. I called it here concrete type adhesive. We have here also a Truss Girder. This is made of round wood. So, and if you can imagine, if you want to connect round by round, in the simple way, you get the cutting surface. It's a 3D structure looking like some potato chips, something like this. So 100 years ago, it's quite difficult to make this, but now we have CNC precision, and so we can do this with this complex geometry. But it's quite expensive. So we had a closer look on the problems in this point and try to make it more simple and even give the architects some more ideas. How can they do something with such a complex joint? So this joint is also ductile. We have a fire protection because this is a special material. It's not inflammable. And then we have the connectors here inside the wood. And you can do as you will any geometry. I'll show you later why. And it's fast and easy to assemble. So I'd like to summarize. We have for large-scale trussed timber structures, we have a problem of the efficient load transfer in the joint. The joint is the weakest point in the structure. We have most of the time a lack of fire protection. When using small cross sections, because the fire protection is getting better if you have a bigger section. And we have a problem with fire protection when we use metal connectors. Traditional is a high assembling effort. That means high cost. And the joint behavior determines the overall design. So the solution is another way of design. That means form follows function and not vice versa. And we can do this here with a hybrid jointing technique. Some examples. We have here the traditional way they try to connect round timber 100 years ago. It doesn't look very special. It's complicated with high assembling and work effort. And on the left picture, you see the roofing of Terminal 1 in Stuttgart Airport. This is steel. In steel, it's much more easier. And the idea was, why don't we follow the nature like they tried to do here and make it less complicated if we have the right connector. So some applications possible with this system I want to show you. This is a spatial structure. You can do also grid shells. This one now is finished already. Starting point for this complicated joint. We neglected this and go for the new design. That means just put all the things you don't want to have not connected, not in the point, do it outside. So we have here the new connector, and then we have here a ductile ring is closing to the close to the timber element, and this timber element is here connected with a special metal connector. So you can do like these truss structures or different ones. For instance, here this is a new one. It's not under construction, it's under design right now. This is a footbridge, and this footbridge is prefabricated, so you can do all this here in the factory, and also all those connected joints, and then just put it together on site. This is a closer look to the structure. We have different parts here. Most of them have equal lengths. So it makes quite simple to do it on site. So this is the truss. We have here the round wound trusses. Then we have here the concrete type adhesive joint. And then we have, of course, the glued-in rod to connect those parts together. So question is now, what is the material? We have used different kind of materials until we got the most successful one. And the most successful ones was a epoxy PC or ultra high performance concrete. With this, we can any complex 3D structure here is productable, because it's a molding process. The material is liquid, and you just can mold it into every form you want to have. We have an efficient load transfer due to high tensile, compressive, and bending stiffness. The stiffnesses of this material is comparable to reinforced concrete you use for skyscrapers. We can do an economical jointing technique with crowding. You have free form, and we have also a low carbon emission in production for this system. So this was for the joint itself, and now we need to connect this piece to the timber. So, and this is done conventional with glued-in rods. I showed you the front page. There, in this structure, in the parasol in Seville, I don't know how many, I guess 2 million glued-in rods used there. And for those who are not familiar with this system, glued-in rods means you have a high tensile strength like a screw. You drill a hole into the timber, and this hole is, according to the design code, 2 millimeters larger than the rod itself. Then you use a special glue. It's a epoxy or UHA resin, and then you put the rod in the hole, and then you fill with the glue, and then you look on the special chambers if the glue come out, and then it should be fully bonded. But you never know if it is, because nobody can look inside. So therefore, there are some restriction in design for this system. Advantage from glued-in rods, it will be also come back after some years to the Eurocode with the novel Eurocode next year. We have high stiffness, we have fire resistance, we have atmosphere resistance, and it looks good because it's hidden inside the structure. And the disadvantages are you need the quality control, and this is the biggest issue if you do bonding on site, the quality control. Yeah, and then some restrictions, design code, etc. So the solution is we're using unconventional embedding materials as shown in the joint itself. And the second thing is we don't use the small hole, we use the big hole. So if somebody is familiar with epoxy and all those adhesives, you will know if you fill it in a big hole, it's an exothermal reaction and it's cooking, and then your structure is gone. So you need some special filler to make it work. So we have done for this some testing. I don't want to bother you with all the details. I put some aspects in the full paper for those of you who are interested in the test results. So we have done first a push-out test to check the resistance here in the structure. We have done a lot of tests, more than 100, and here some configuration. We have took into account the fiber orientation, that means parallel and perpendicular to the grain, and also the drill hole diameter. Then we have done same as a pull-out test to obtain the withdrawal resistance. And here we have also different parameters, the drill hole diameter and steel grade, of course, yes. Some results here, the embedding and the withdrawal stiffness is increased with the drill hole diameter, surprisingly, because we don't use a commercial adhesive itself. And it was increased perpendicular to grain. That means the wood fibers act like additional reinforcement, you know, from reinforced concrete. So failure in the specimen was nearly overall in shear and also cohesive failure in timber, and therefore we can use interface models and to check with design models for further design. We have done this here. This is a composite friction models from Xu and Needleman. It's done some years ago for soil mechanics, and is also working very well for this problem. And this combined with fracture mechanics, where you have adhesion and separation part depending on fracture energy. Then you can do this. This is with model with ANSYS and verify the testing. So next question is how to produce this. So we have the design idea from the architect, can do this with a computer drawing. And usually we do this with Rhino. and then export the different geometries in the finite element code, do the calculation with the model, and then after verification you need to check or change something in your structure, and then if this is done you can mill it, produce the negative, and then the joint is molded and casted with the special grout. Those pictures are from the lab, but meanwhile we do this in a automated process. You have here the formwork, the negative formwork, then the grout, and result is the joint geometry. And this can then combine together with the different parts of the timber. I like to conclude my presentation. Composite behavior between timber and concrete type adhesive can be assumed as rigid and shear resistant. Design of composite components and complex 3D geometries and joints with the proposed numerical model is possible. The proper description of the damage behavior with the numerical model is verified by the lab tests, and it's commonly accepted. Larger drill hole diameters cause in the higher bond line quality. It's the difference. If you have a very small hole, you cannot see what's going inside. If you have a big hole, just fill it and then have a look inside. And so we neglect miscuing. And at last, innovative design of large-scale timber structures is possible for truss structures, for bridges, and whatever you want to do. I want to give you a short outlook. Those kind of structures are possible here, and we work together with interior design and architects, and they have a pop-up with a lot of ideas when they have something they can go a further stage from the drawing into the constructions. Andrew Walk, maybe some know who it is, said 2 years ago or last year, the 21st century will be built in wood, and he made a first step to do this in London and in the UK, and I hope he's on the good way, and he's right. And so I want to conclude with this sentence and hope I can bring a little bit of ideas here to Asia. And I was just 2 weeks ago in Kuala Lumpur, where we have a cooperation with the university, and they just started with glulam and manufacturing of such new type structures. Thank you very much for your attention. Wood itself is a sustainable material you can imagine, because in the timber is stored more carbon in the material itself than you can put in the atmosphere on production. So if you go for timber buildings, this is the most sustainable building you can have now in civil engineering and in architecture. If you go for a concrete building, there's I don't want to talk hours and hours about this.
Prof, are these joints commercially available in Asia?
Not yet. But if you want to have a contract, we can do some company set up, of course.
I noticed that in your modeling, you use your finite element method, actually loaded joint. Now, do you have an experiment also or numerical model with the combined sources like axial shear bending?
Combined? Of course, yes. This is a 3D model. It's a 3D fracture model in ANSYS. So you have all those phenomena combined in this model. It's a multiplasticity model with all this kind of stuff you want to have. It's a commercial product and it's common used in university because it's a very, very complex program. I know my colleague, he's in Berkeley. He moved from Weimar, doing this earthquake design modeling also with this program.
My name is Father. I'm from Georgia.
Mm-hmm.
Well, I'm wondering why we use timber compared to steel. Our countries, we don't have much wood. So using timber is very, very much costly than compared to steel.
I disagree. Steel prices are rising up every year because China is buying any single nail they can get. And we have a sustainable forestry in most countries of the world. And we have enough of wood, birch, and others. And so in the past years, the wood prices are falling. Yeah. And you need, depending on what you want to have, what kind of structure, especially for residential buildings, it's quite nice. Together with the architect, you can have some eye catcher, or you do the structure in reinforced concrete and do the facading with timber elements, or you go for commercial buildings. A lot of commercial buildings, they want to have the green thumb as a contractor or the owner, and then the architects do most of those buildings with very nice timber structures. Yeah. For multi-story buildings.
Can you put some light on the performance of such joint under dynamic loads, like wind load or seismic loads?
Seismic loading?
Yeah, and wind load.
Yeah. Therefore, we have the ductile ring. And if the structure is under vibration, then it's a ductile joint. So it's no brittle failure. So you can move this a little bit, and so this the dynamics is compensated in the joint.
University of Technology. You showed us the joint between this concrete type adhesive with wood. Concrete is typically stiff material, and if we put together weak wood and stiff material, we obtain high stress concentration, especially during the shear test, during pull-up.
Yes.
The higher stiffness of the material, of joining material, the higher stress concentration. So if we apply such stiff joint to the weak material, we obtain quite weak detachment of the concrete in timber. So the fiber motifs in timber. Can you tell us something about Young modulus of this concrete and ultimate strength?
The MOE of this concrete type is not the concrete itself. adhesive is about, the MOE is about 30 megapascal. So compared to ordinary concrete, you're using
40 megapascal.
30, 30.
And ultimate strength?
Is 100, 100 in bending is about 5.5, and in compression is 110
You mean percent?
megapascal.
No. I asked about ultimate strength in percent.
The ultimate strength,
Elongation.
elongation.
Elongation. Ultimate elongation. If you measure.
I need other classes to see any elongation in this material. Is it's about I don't know, maybe 0.1 or 2%. Yeah, so it's quite stiff. That's why it's connected with the high steel grade rod, yeah, and the ductility is giving in the surface between the rod and the ductile ring. Because there's no bending, nothing in this material. Further questions?
PC, and I was just wondering which company produced it, or where did you get it? What did you produce?
The material?
Yes, material.
We have a license of this special material. I'm doing research for new type of structures and also for rehabilitation with this epoxy, and starting 10 years ago with this topic, composite materials. But it will become commercial available. So, any other questions? Yes?
May I ask another one? Can you tell us something about curing time of this concrete?
Curing time, okay, this is another advantage. If you have reinforced concrete, you need at least 2 weeks to put some load on it, and the full strength is defined after 4 weeks. And this material, it's a adhesive. You can put, it starts curing around 1 hour after casting, and has the full 90% of the full capacity after 1 day. So it's quite fast producing. Yeah. And even if you use this in construction, you can go one step further. Yeah. So it's a big advantage for the construction company in terms of cost for formwork, whatever you need to bring to the. So I cannot see any other questions. I'd like to thank you for your attention. Thank you very much.